Hey everyone, welcome back. Last time we were talking about this method of finding the volumes of certain solids, right? Solids of revolution. And we called it the DIS method or the washer method. So let me just draw a quick picture to remind you what we were talking about last time. So we have this region. We revolve it around the x-axis. It generates this solid. This solid would have a sort of funny shaped hole in the middle. What I want to pay attention to now is the process that we would have gone or that we went through to derive our formula. And so the idea is we want to take an approximating rectangle and just think about what would happen if you revolve that rectangle about the x-axis. Well, what it would do was it would create a washer, right, which is really a disc with a hole removed. And so the idea was if we take a bunch of approximating rectangles that fill out this entire region, revolve those about the x-axis, that gives an approximation of the shape of the solid. By adding up the volumes of these washers right here, that gives us an approximation of our actual solid. By taking the limit, we actually got the formula for the DIS method. Now, today what we want to do, instead of revolving around the x-axis or axes that are parallel to the x-axis, I want to take the same region and revolve it around the y-axis. Now, the approximating shape, if we use a rectangle like this, the approximating shape is going to be different. Now, if we just take this rectangle and revolve it about the x-axis, what we're going to get, let's see if I can draw it, is no longer a disc. In fact, what it is, so let's see here. Is what we call a cylindrical shell. So this thickness right here, that thickness right there is delta x. It's the thickness of that rectangle. So as that rectangle sweeps about the y-axis, it carves out this shape right here, which is a cylinder with a cylinder removed from it, right? That's what we call a cylindrical shell. And so today, all right, let's write that down, cylindrical shell compared to a disc or a washer. Right? So depending on which axis we revolve about, it generates a different shaped solid, and so it creates, and this is going to give us a new method for finding volumes of certain solids. Now, all right, so what I need to do then is I need to come up with a formula for the volume of a cylindrical shell. Right? So the volume of a cylindrical shell is going to be, well, you can think of it as, let's say, outer cylinder minus inner cylinder. So let's see now. Okay, so there's two different radii going on here. So let's take R1 to be the radius. Sorry, my drawing's not that good, but let's say R1 is the radius going from the center out to the outer the outer shell, and then R2, let's put it here, will be the radius going to the inner shell, right? So the volume of a cylinder, pi times the radius squared, so the outer cylinder has radius R1, so it would be pi times R1 squared times h, where h is that height right there. And then for the inner cylinder, we're going to have a pi R2 squared times h. And then I want to factor this. So this is pi, I can factor pi out of each piece, R1 squared minus R2 squared, and then I can factor an h out of each piece also. And then I'd like to factor this a little bit more, so this is pi times R1 plus R2 times R1 minus R2 times h. This is just the difference of two squares here, so I can factor it this way. And then I'd like to do one thing that's not going to be completely obvious. I'd like to multiply and divide by 2. So what we're going to get is a 2 pi times r1 plus r2 over 2 times r1 minus r2 times h. Right? So keep that formula right there in mind. And now we're going to go back and we're going to actually go through the details of deriving a formula for finding volumes. It'll be called the method of cylindrical shells. Right? And we'll need that formula in just a minute. So now let's set up everything precisely. So let's let R be the region bounded by the graph y equals f of x, y equals g of x, over the interval from a to b, where we need our functions to be continuous, so where f of x and g of x are continuous. And then let's let S, I'll draw the picture in just a minute, so let's let S be the solid generated by revolving R about the y-axis. All right, so here's the picture. I'm going to have to erase this formula. Well, I'll try to leave the bottom portion of it. In fact, let me move it up to this corner here. So our formula is going to be 2 pi times r1 plus r2 over 2 times r1 minus r2 times h. Okay. So the picture goes like this. There's A, there's B. I'm thinking of y equals f of x. The f of x function is the upper one, and then y equals g of x is the lower one. So here's our region. We're revolving around the y-axis. Okay, so now I want to do the usual setup. So step 1. Right, we've seen this a few times now. Partition the interval from a to b, so that's going to be a equals x0 less than x1 less than dot 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 less than x of n equals b into subintervals of length delta x. So what are we doing then? We're chopping the interval. I want to keep my picture simple, so I'm chopping the interval, in this case, into 3 separate pieces. These are supposed to be equal length, so let's do a better job there. Something like that. So there's an x1, there's an x2, b is x3, and a is x0. Then the next step is to pick a point in each of these subintervals. And in this case, now remember, it does not matter where we choose the point. And so in most of the derivations that we do, we will just pick the point at random, but we can choose it wherever we like. And in this case, I want to pick it specifically, I want it to be the midpoint. So let's let xi star equal, well, let's see, the midpoint. How do you compute the midpoint? You add the endpoints and divide by 2. So xi star is going to be xi minus 1 plus xi over 2. So that's the midpoint. And let r sub I, remember we're trying to create rectangles here, so let r sub I be the rectangle with height. So what I want to do at each midpoint, I want to go up, hit each of the graphs. That's going to determine the top and the bottom of my rectangle, like that, like that, and like that. So it's going to have height f of xi star minus g of xi star, and the base well, the base is going to be delta x. Okay, so there's the second step. We choose points in each interval. In this case, we chose the midpoint. Use that to determine rectangles. Now what I'm going to do is I'm going to revolve each of those rectangles about the y-axis. So the result of revolving r sub I about the y-axis is, well, it's going to be a cylindrical shell. So this is a cylindrical shell of volume. So now I want to use this volume form that we have right here. So it's going to be 2 pi. And then look at right here. This is the average of the radii, and that's exactly what we have right here. So it'll be 2 pi times xi star. I wish I would have written this in opposite order. So I want to put the h here next. So h, the height, is going to be f of xi star minus g of xi star. And then the very last piece, which I have written here, R1 minus R2, that corresponds to the difference between these two things right here, which we're now calling delta X. Right? So the volume of a single cylindrical shell is right there. Right, so we factored things in a funny way here to make it work out nicely for our formula when we're actually using approximation by rectangles. So now what we have is that the volume of S is approximately equal to the sum of the volumes of the cylindrical shell. So that'll be sigma I equals 1 to n 2 pi times xi star times f of xi star minus g of xi star times delta x. And so now if we want the actual volume, so let's call this step 5, the volume of S is going to be the limit of this right here, this Riemann sum. And I'm just going to write it. So if you imagine taking the limit, what we get whenever you have continuous functions, can be computed as a definite integral. So we'll get 2 pi times the integral from a to b of x times f of x minus g of x dx. Right? Just take the limit as n goes to infinity, and here's what we get is this definite integral. So this formula right here is called finding volume using the method of cylindrical shells, or what I just usually refer to as the shell method. So now we have two different methods for computing volumes. We've got the disk method and the shell method. Now, one thing, before I erase this, one thing that's important to sort of be aware of. Each of the pieces in here have some meaning. So x, what is x? Well, oops, I started to erase my picture. X is a random point inside here. We use the midpoint, right? So this x right here refers to the radius, right? Think of x as the radius of our cylindrical shell as it gets very, very, very infinitesimally skinny. F of x minus g of x, that corresponds to the height. So in this formula right here, you can see radius times height. Right? And that'll be important a little later on. So let's try some examples. So first example, and let me just draw the picture here. And all I'm going to be caring about is the setup, or that's what I'm going to do in these problems. I'm not going to actually compute the integrals. So let's first take this one right here. This is the graph y equals square root of x. over the interval from 0 to 1. I want to take that region and revolve it about the y-axis. So according to the shell method, the resulting volume is going to be 2 pi times the integral from 0 to 1. X times top function minus bottom function. In this case, the top function is square root of x. The bottom function is just the x-axis, which is 0. Right, so in the end, then it would just be 2 pi integral from 0 to 1 x square root of x dx. This leaves us with an easy integral. What I want you to do is be clear on what the setup is. When you see a region like this and you revolve it around the y-axis, right, the setup for the shell method gives us this formula right there. So another example. So remember this one, we've seen this little sliver before here. So this upper graph is y equals x squared, and the lower one y equals x cubed. Now I'd like to take this little shape and revolve it, instead of about the x-axis, let's go about the y-axis. Now if we set up the integral for the volume, it'll be v equals 2 pi integral from 0 to 1 radius times height. X top function minus bottom function. So that computes the volume. Okay, so now let's take the following region. So here's our next example. This lower graph is y equals 4x squared. The upper graph is 2x plus y equals 6. Now, what I'd like to do is take this region and revolve it around a couple of different axes. And by the way, I computed the intersection points. That's a -3/2 there, and that's a +1. Now, if I take this region and revolve about the x-axis, then we'd be using the disk method. So let's first do about the x-axis. In that case, we use disks. And the volume then is going to be pi times the integral from -3/2 to 1. And I need to solve here, so this is going to be y equals 6 minus 2x. So 6 minus 2x, that gives us the outer solid, minus the inner solid, like that. Now, what I'd like to do is change things up a little bit. So now let's revolve about the line x equals 2, which is the line over here. Now, if we take an approximating rectangle like that and revolve it about the line x equals 2, it still generates a cylindrical shell. So we're going to use the shell method. And now, since we're not going about the y-axis, we need to see how things adjust. So if you were to take a cylindrical shell, take a rectangle, revolve it to generate our cylindrical shell, what changes in our setup? Well, the thing that changes is our radius. Instead of measuring to the y-axis, we're measuring to this axis right here. So our radius, the radius of our cylindrical shell, is now that distance right there, which is measured as 2 minus x. So the radius changes. So the volume is going to be 2 pi times the integral from -3/2 to 1. And now instead of putting an x, remember that x stood for the radius, we need to adjust our radius. It will be 2 minus x times the height, which is top function, 6 minus 2x, minus bottom function, 4x squared dx. So we want to generalize things now with the shell method also. Instead of revolving about the y-axis, we want to be able to revolve around lines that are parallel to the y-axis. And so we need to understand how things change, how things adjust when we shift our axis. Okay, for our next example, what we're going to have, this is the graph x equals y squared on top and y equals x squared on the bottom. And I want to revolve this region, right? So we've got this region right here. I'd like to revolve this around about a couple of different lines. Now, what we see here is a situation where we're going to be able to use both the disk method and the shell method. And so before we go on, I want to talk about this concept of legal rectangle. When you draw a particular diagram, a particular region that you're about to revolve around some line, remember that I always draw this approximating rectangle. Now, my approximating rectangle is going to be legal if it hits both graphs exactly one time. So in this situation right here, notice if I draw my rectangle vertically, it hits both graphs exactly one time, and no matter where I put it inside this diagram, right, it meets exactly one time. So vertical rectangles, we say, are legal. But also now, if I draw a horizontal rectangle, no matter where I draw it, it hits each of the graphs exactly one time, and so those horizontal rectangles are also legal. And let's compare this. Before I do this example, let's compare with the picture that I drew just a minute ago. It looked like this. Now, if I draw a vertical rectangle, no matter where I draw it, that rectangle is going to hit both graphs exactly one time. Vertical rectangles are legal. But if I draw horizontal ones, well, okay, look at when I draw a horizontal one down here, it hits both, it only hits this graph, the lower graph, and it hits it twice. Up here they're legal, down here they're not. And so in this region, only vertical rectangles are legal, horizontal ones are illegal. So here's the rule of thumb, and I'm going to put this down before we actually do our example. So legal rectangles, if they are parallel to the axis of rotation, that means that you're using the shell method. If perpendicular to the axis, then you're using the disk method, right? And so these concepts right here are going to allow us to deal with situations like this where we can revolve around various axes and both methods are actually going to be legal, or they'll be workable. Okay, so what I want to do, let's revolve about, let's go about y equals minus 1. So that's that line right there. And what I'd like to do is set up integrals using both methods. So first, let's use disks. If I use disks, that means that I want my rectangle to be perpendicular to the axis of rotation, so it's going to be a vertical rectangle. Notice that it has thickness delta x. That tells us that we're going to be integrating with respect to the variable x. So using the disk method, we're going to get pi times the integral from 0 to 1 And then it's going to be, let's see, the outer solid. That's going to be, oh, and by the way, I need to solve here. This is y equals square root of x. So the outer solid, square root of x minus -1 quantity squared. Subtract away the inner solid, that's going to be minus x squared minus -1 quantity squared dx. Right. If I use the shell method, so for shells, now we're going to be working with horizontal rectangles. These have thickness delta y, which means I'm going to be integrating with respect to y. So it'll be integral from 0 to 1, and I should point out this is really just coincidental. When I did the dis method, I'm measuring along the x-axis 0 to 1. This 0 to 1 for the limits of integration are being measured along the y-axis. They just so happen to match. So 2 pi integral from 0 to 1. Radius, let's see now, what's my radius? Well, my rectangle's at position y. I need to measure the distance from that position to the axis of rotation. So that will be a y minus -1. Yes, I know it's y plus 1 in the end, right? But I'm trying to show you who all the pieces are to this, right? The setup is the important part. And then we need top function minus bottom function to get the height. Remember, up is in this direction. So it's going to be square root of y minus y squared dy. Where here I had to solve, so that's x equals square root of y. All right, so the point here, there are going to be regions for which both horizontal and vertical rectangles are legal. In that situation, you can use either the shell method or the dis method. Sometimes it really then just becomes a matter of taste, which one you prefer. So let's do one more example, and then I'll write down the general procedure for the shell method also. So let's see now, I've got a parabola. It's a little off kilter though. It goes from -2 to +1, and the formula for this is y equals x squared plus x minus 2. X squared plus x minus 2. Okay, so I want the region between that parabola and the x-axis, and then I want to revolve this around a couple of different lines. So let's first go about the line y equals 3. Well, okay, so the line y equals 3, that's up here. And before we go any further, we need to decide now, are horizontal rectangles legal? No, definitely not, right? They hit the same graph twice. Are vertical rectangles legal? The answer is yes, right? And so no matter which line we revolve about, we're always going to be using vertical rectangles, and that will determine which method we use. So if we go about the line y equals 3, our rectangles are perpendicular to the axis. That means that we're using the discs, so the disc method. So discs, the volume is equal to pi times integral -2 to +1. Outer solid minus inner solid. Now the parabola determines the outer solid. So this is going to be 3 minus x squared plus x minus 2. All that squared. And then we subtract away the inner solid, which will be a 3 minus 0 squared dx. Now let's go about one more line. Let's do this line over here. Oh, yeah, that's fine. Okay, so we'll go about that line right there. That's the line x equals 2. In that case, our rectangles are parallel to the axis of rotation, so we're going to be using shells. The volume is equal to 2 pi, integral from -2 to +1. the radius, so now think about it like this. I choose a rectangle at position X to measure that radius. It's going to be larger number minus smaller number, so it's a 2 minus X. Top function, which in this case is the x-axis, so it's 0, minus bottom function, which is x squared plus x minus 2. Okay, so it's going to be important now to understand shells versus discs. So when you do your homework, in the beginning it'll say, okay, use the shell method. It'll tell you which method to use. In the later homework problems, it's going to say use whatever method. Remember this concept of legal rectangle, and then parallel versus perpendicular. That's going to tell you which method to use. Let's end with just the general procedure. For the shell method. So if I take a region that looks like this, and we take a rectangle of thickness delta x at position X. There's two possibilities. I could have an axis of rotation that lies to the right of the region, also one that lies to the left. And so if we go about the line x equals c, we'll have 2 pi integral from a to b. And now what's our radius? Well, our radius is going to be measured from position of the rectangle to our axis, so that's going to be x minus c. Top function, oh, I should have labeled this, so this is y equals f of x, and this one's y equals g of x. So the height will be f of x minus g of x dx. If we go about the line x equals d, what we get is 2 pi integral from a to b. D minus x, that's the radius now, measuring this distance right here. Top function minus bottom function dx. All right, so notice the order of subtraction changes depending on whether the axis is to the left or the right. I don't think you should memorize these formulas. I think you should understand why they're true. It's okay if you want to memorize them, but really it's important to understand why they work and also to be able to distinguish between shells versus discs. Okay, so do your homework, and if you have questions, make sure come to office hours. This is a concept that can be a little bit confusing at first for students, but once you get it, once you see the difference between shells versus discs and understand the two general procedures, the one that I gave you for discs and the one for shells, right? This should click, and you should hopefully won't have problems doing it. Okay, so we'll see you next time.